Waves at the surface of the ocean are among the most impressive sights that nature can offer, ranging from the chaotic motions in a violent hurricane to the tranquility of a gentle swell on a tropical beach. This is a kind of romantic quote. If the word waves is taken to mean vertical motions of the ocean surface, then wind-generated gravity waves are only one type amongst a variety that occur in the oceans and along the shores of the world. The scientist is mostly interested in the dynamics and kinematics of the waves, how they are generated by the wind, why they break and how they interact with currents and the sea bottom. This graph presents some types of waves by their frequency and period. Important for us are those wind-generated waves. In these frequencies or periods ranging from 0.1 up to 10 or a bit more seconds, the capillary waves, the swell waves, and the wind seas are among the most energetic waves on the ocean. We will see some more information about them. Regarding wind-generated waves, there are three of them which are important to be noticed. The first one are the capillary waves, that are waves with short periods, shorter than 1/4 second, that are affected by surface tension. The wind sea are waves generated by local wind, with periods larger than 1/4 and up to 8 seconds, which are irregular and short-crested. The third of them are the swell waves. These are waves that leave their generation area and take on a regular and long-crested appearance, usually with periods longer than 8 seconds. Ocean waves. Waves represent physical processes that are very efficient at transporting energy over long distances, typically without permanently disturbing the environment through which they travel. Wind action takes place over the ocean. This action is about wind direction, wind duration, and wind velocity. This occurs over a limited portion of the ocean that is called fetch. And under the wind action over the fetch, wind seas are generated. Wind seas propagate beyond the fetch, and the waves organize themselves in the form of swell waves. As the wind blows across the ocean surface, it generates disturbances on the sea surface that render local patches of the surface out of hydrostatic equilibrium with the rest of the sea surface. Gravity acts to restore this equilibrium. Waves represent physical processes that are very efficient at transporting energy over long distances, typically without permanently disturbing the environment through which they travel. Gravity waves represent a type of mechanical wave in which the Earth's gravity provides the restoring force that drives the dynamics of the waves. It is normal to confuse any elevation of the sea surface to be a wave, but this is incorrect. In a time record, the surface elevation is the instantaneous elevation of sea surface relative to some reference level. In such a record, a wave is the profile of the surface elevation between two successive downward zero crossings of the elevation. Waves in the ocean are quite irregular and nonlinear. Sine wave theory is a good approximation to describe some important wave parameters. From this theory, this expression can be derived to describe the evolution of sea surface as a function of location in space, x and y, and time, t. These are some basic wave parameters. The crest is the highest point of a wave. The trough is the lowest point of a wave. The wave height is the vertical elevation of the crest above trough. Amplitude is the half of wave height. The wavelength is the horizontal distance between crests or troughs. The depth is the elevation below the still water level towards the bottom. Wave height, or h, is the vertical distance between the highest and the lowest surface elevation in a wave. The standard unit is meters. This parameter is mostly used in energy-related projects because the wave energy is proportional to the square of h. Significant wave height, hs, is defined as the mean of the highest one-third of the waves in the wave record. The value of this wave height is close to the value of the visually estimated wave height. It's very used to characterize sea conditions. Wave period, T, is the time interval between the start and the end of the wave, the interval between one zero down crossing and the next one. The standard unit is second. The wavelength, L, in deep waters is the horizontal distance in meters between two crests and can be defined as L equals 1.56 multiplied by the square of the period. Celerity, c, is the speed at which the waveform travels and can be defined as c equals L under t. Wave energy, E, the energy of a wave is related to the square root of its height, and it's often measured in terms of wave energy per unit surface area. And continuing with the basic wave parameters, the relationship between wavelength and period is known as the dispersion relationship. and is expressed as sigma. And sigma is the square root of j, k, tangent of kh. Note that the strength of gravity is very important and reflects its role as the restoring force in surface gravity waves. The wave phase speed or celerity is defined as the speed with which a point of constant phase, example the wave crest, moves through the water. As we saw, the celerity equals the length over the period and can be also written as a function of wave period. In deep waters, c, the celerity, equals the gravity multiplying the period over 2 pi. It's important to note that in deep water, the phase speed of waves is dependent on the period with longer waves traveling faster. This behavior explains the origin of the dispersion relationship, because in a collection of different waves, they will sort themselves out of generation area, with the longer waves propagating away faster than the shorter ones. The graph relates the ocean's wavelengths in the x-axis with their speed that can be better understood with the y-axis on the right. And inside the graph, there is a curve representing the period. It is important to note that we already saw that the wave velocity or celerity increases with increasing period and wavelength. So the greater the wavelength and the greater the period, the faster movement of waves. The motions of water particles below a progressive surface gravity wave are called orbital motions. Look at those images. Note that the orbital motions decreases rapidly with depth, so this wave isn't affected by the seafloor. The orbital motions, half a wavelength below the surface, are mere 5% of those at the surface. Note also that the pattern of orbital motions is quite circular near the surface and becomes quite elliptical and reduced with depth. The waves propagating above the ocean experience different conditions and can become quite different depending on which depth they are propagating over. Usually, the limit for the deep water approximations validity is reached when the water depth is greater than half a wavelength. In these conditions, waves are not influenced by the ocean floor. The changing wave conditions occur when they start to feel the bottom. This occurs when the depth is lesser than half the wavelength. In such conditions, we use the term intermediate waters or intermediate waves. Finally, when waves reach depths less than 1/20 the wavelength, they become shallow water waves. Ocean waves spectrum. If we look out to the sea, we notice that waves on the sea's surface are not simple sinusoids. The surface appears to be composed of random waves of various lengths and periods, and this is the concept of the spectrum of ocean waves. The spectrum gives the distribution of wave energy among different wave frequencies of wavelengths on the sea surface. Therefore, we can represent a local sea surface by a linear superimposition of real sine waves, having many different wavelengths or frequencies and different phases traveling in many different directions. These are the interference pattern between ocean gravity waves. They can be constructive, destructive, and mixed. Constructive interference, on the left, occurs when waves of the same wavelength come together in phase, crest to crest, and trough to trough, producing waves of greater height. Surfers may call this a set. Destructive interference, on the center, occurs when overlapping waves have identical characteristics but come together out of phase, resulting in a cancelling effect. More commonly, waves of different lengths and heights encounter one another and produce a complex mixed interference pattern on the right. Coastal process and beach dynamics are strongly governed by the action of waves. The long-term wave forcing that affect the long-term beach dynamics can be defined as wave climate. Wave climate is the statistical distributions of certain sea state parameters at a specific location over a particular period of time. The Beaufort scale is a scale of wind intensity used since the beginning of the 19th century. Today, the Beaufort scale is a scale that describes the expected sea and land conditions among 13 descriptors, from calm to hurricane. Let's see what's next. The Beaufort scale is a scale of wind and the expected sea and land conditions. 13 stages are ranging from 0 to 12. In this table, there are descriptions of the stages ranging from calm to hurricane, the wind speed ranging from 1 to greater than 118 kilometers per hour, and there is also the description of sea and land conditions, ranging from flat seas with smoking rising vertically up to huge waves and sea completely white and widespread damage inland. Let's see some more about these stages. And this map shows the geographical distribution of the annual 90th percentile wave height for the 1958-1997 period. The areas with the strongest winds and higher waves are in the North Atlantic, between Iceland and Canada, and in the Southern Ocean. And this map shows the annual mean wave power density in colors and the annual mean best direction in the arrows. This demonstrates that most interest for wave power is on the west coast of land masses, as waves flow primarily from west to east. The wave power is predominantly found between the 40th and the 60th lines of latitude, north and south, with a larger proportion in the southern hemisphere. So now we are going to talk a little about wave climates. This is a sketch of databases in an idealized coastal stretch. Sources of wave data currently available may be conveniently be considered under three main headings: instrumental, including remote sensing from satellites and buoy data; hindcast, that are estimated from wind field analysis, this is very common; and visual wave observation from ships, usually from ships. In general, instrumental data are preferred where possible because they are considered the most reliable. However, in practice, it is often necessary to use hindcast or visual data because of the greater availability, covering long periods of time in most sea areas of the world. Now, about instrumental data of wave climate, measurements of waves have been recorded for many different purposes by many different agencies, using many different types of instruments. And the resulting data have been analyzed and archived in many different ways. Weather buoys are instruments which collect weather and ocean data within the world's oceans. In those images, there are two examples of weather buoys. The left one is a moored buoy, and the right one is a drift buoy. This is a printed screen of the Brazilian National Program for the Observation of the Ocean. Today, 22 moored buoys, like this one on red dots, and 297 drifting buoys were launched. You can see some of them in these blue paths. This program aims to collect data for many scientific community goals, for Navy operations, and also to provide improvements on marine climatological forecasts. And this is an example of an operating buoy in Brazil. There are some information and some results. The results include the position information, longitude and latitude, the wind speed, the wind direction, the wind gust, the atmospheric temperature, the atmospheric pressure, the dew point, humidity, significant wave height, maximum wave height, wave period, mean wave direction, and a spreading index. And now talking about hindcast data. Wave data can be derived from wind field information by the use of methods known as hindcasting. A wide variety of methods is available, ranging from simple formulae for estimating wave heights at a given site from the knowledge of the wind speed, fetch, and duration to numerical models for translating wind field time histories, covering large areas into corresponding wave field information. Most hindcast wave data used in the world comes from two major sources. The first one is the European Centre for Medium Range Weather Forecast, ECMWF, that develops the IFS or Integrated Forecast System and their derived one, that is the wave model. The second major source is the NOAA, National Oceanic and Atmospheric Administration, that develops the GFS or Global Forecast System and their derived WaveWatch 3 model. Obviously, there are other forecasts and hindcast models in development by public and private organizations around the world. Those models compete for the better and most accurate numerical models, and to provide reliable hindcasting, nowcasting, and forecasting results. In this context, hindcasting, nowcasting, and forecasting are methods to implement oceanic and atmospheric equations in order to provide meaningful results for the analysis of the past, the present, and future sea state conditions. And here is some animated example of hindcast data along the South Atlantic Ocean. And finally, in this graph, there is some comparison of buoy data, the black dots, and some forecast data, the blue line, for somewhere in Portugal. The red line is the hourly moving average of the buoy data. There is some disconnection that is clear for the lowest waves when the forecast model overestimates them. And as the waves increase in their heights, the model tends to underestimate them. It is quite important to know the magnitudes of this asymmetry. Let's practice. A 5-year wave climate hindcast data is provided. Use a spreadsheet to open it and to do some basic statistical calculations to find out the maximum, the average, the minimum, and the standard deviation for each variable. Then create a graph using wind speed, significant wave height, and wave period variables. Write a small report to present your results. The simple report must be sent to my email address. Good luck! And this is enough for today. See you soon. Take care and be safe.